book, FEA book, and on July 17th, I did this problem. It was the first time that I was introducing to the shell problems. And I mentioned that there are two different ways to do these problems. One of them is to use the surface extraction method, and that's exactly how this problem was done in the book. And then after I do that, I go briefly, very quickly through the alternative way of creating the surface that you need directly. The problem that we are going to consider is let's think about it as a folded sheet metal, like so, that the bottom edges are clamped and the surface on the top is pressurized. Now, keep in mind that first of all, the assumption is that the entire sheet metal has the same thickness. Okay, I will in one of the future segments I will explain what happens if the sheets have different thicknesses. In any event, you can see that in this problem you have two planes of symmetry, and when the symmetry is used, only 1/4 of the model, the quarter of the problem is modeled, and that's what's shown on the right-hand side of your screen. The first method is going to be the shell extraction method. So I would make a box this size, not the size of the original problem, although it is possible to make the size reflect the original problem and then start cutting it. However, since we know where we're going, the box that I'm going to make is 2 inches long, 1/2 inch high, and 1 inch wide. So let's now move to the Catia program. This is all a part, so single part. So I'm going to start with a part. Okay. So and let me switch to part design, because I'm going to make a box here. On this vertical plane, I will sketch a box the size that we want. And let me see now. The dimensions were 2 inches this way, 1 inch this way. I'm sorry, 1/2 inch in the vertical direction. Exit, and now pad it by 1 inch to reflect the size of the geometry that we want. Now, at this point, I would like to extract the top surface and the bottom surface, the vertical surface. Okay, so in order to extract surfaces, we have no choice but to go to the wireframe and surface design, so mechanical design, the third workbench from the bottom, and look for the extraction. The extraction is in the operations toolbar, the third icon to the right. Now keep in mind that this actually has two elements in it. The one that we want is extraction, right there, surface extraction. You click on it, you select the top surface, it turns green, and then repeat it. You select the vertical face, and it turns green. Now we have two surfaces here, and I can hide the box so that you're convinced actually these are two surfaces. These two surfaces, because we use the surface extraction method, they don't talk to each other unless they have the same, unless we join them. Okay, the join operation, you already know where it is. You can see it's right there in the operations toolbar. You click on it, the horizontal surface and the vertical surface, and then we say okay. We now apply material material to the problem. Let's say it's made out of steel on the part, and obviously the joint is going to inherit that too. So we are done as far as the making of the model is concerned. But keep in mind that the solid box that we made in order to extract these surfaces is in hiding. It's in the background. All right, we switch to generative structure analysis. Immediately, what you see is that the box, oops, try again. Immediately, you see that the box that's in hiding is meshed with solid elements. Here's solid elements. We don't want these elements because we're supposed to do this problem with shell element. And also keep in mind that if you, on a test, you are asked to use the best element to do this problem, and you use solid elements to do that, uh, basically you ignore an instruction, you get no part marks. Okay, so I'm going to have to delete this element. We don't need it. And also a 3D property was automatically created, so I have to delete this one too. Good. Shell elements have to be meshed manually with you. So here is the shell element shell element mesh, and Catia calls it octree triangle mesh here. I call it shell. You should know what shell means. All right. So you click on it, you select the surface. Because they're joined together, both surfaces are meshed simultaneously. And I'm not going to change the size of the element. I'll leave it the way it is for now. And we now have to specify the thickness of this sheet metal, folded sheet metal. So the thickness of the shell elements are described in the 2D in the model manager under the 2D property. You click on it and you select the surface and you put the appropriate thickness in it. So I put down point here, 0.1. Let's make it how about 0.01? That's 100th of an inch. Okay. And if you want to see the mesh, you follow the instruction, the usual instruction. You put the cursor on nodes and element, right click, and mesh visualization. And the mesh is going to be shown to you, and you can see that when you deal with surfaces and shell elements, for visualization purposes, there is no thickness right there. There is no thickness to these things. You can see. All right. For the rest of the problem, I'm going to deactivate the mesh. And let's see what constraint do we have. So first of all, the bottom edge is clamped. Okay, it doesn't matter if this is only 1/4 or not, it's still clamped. Now, the edge that you see here, this horizontal one and this vertical one, they lie in a plane of symmetry that is parallel to the XZ plane. You can see that from the compass. So you have to apply the proper restraints there. User-defined restraint, this edge and that edge lies in the XZ plane, therefore there is no displacement in Y, and once you know that, the rotations are exactly the opposite. We have to do the same thing for this side. So user-defined restraint, once again I'm going to clear these check boxes, and this is the edge that you want to take, and that edge lies in the YZ plane, therefore there is no displacement in direction X, which is direction 1, and rotations are exactly the opposite. What that means is that if the translation is checked, rotation for that must be unchecked. If the translation is unchecked, the rotation for them must be checked. Let us apply a pressure. I don't know the pressure in the book. Let me put 100 psi here, because I don't remember exactly what the pressure is for this problem. So I'm going to click on it and put 100 psi. Notice the direction is correct. If you were actually applying the pressure at the bottom so that this would rise, this surface would rise, then you have to turn it into negative. All right, let's go ahead and run it. So we're going to go run. We can look at the deformation. There it is. And if you animate it, this all looks reasonable. Okay. Let us also look at the deflection, displacement. And notice that the deflection of this beam, the maximum deflection, is shown to be 2.55 inches. Now, this is a huge deflection. It's impossible to have an elastic response for the size of the geometry that I gave you to be 2.55. Keep in mind that this left edge is only half an inch. And how can the deflection here at the center be 2.55 inches? That's impossible. Which means that Catia will do what you ask it to do, but it may not be meaningful. In here, of course, one way to at least try to salvage this problem is to give it a bigger thickness. So I'm going to double click on that, and instead of 0.1 inch, I'm going to turn it into, instead of 0.01 inch, I'm going to take it 0.1 inch. 0.01 0.01 inch may be the size of a aluminum sheet, for example, the foiling sheet that you use for cooking purposes. So what we did, we increased the thickness by a factor of 10, and we're going to run it again. And now look at the deflection one more time to see if it's meaningful. And now you can see it's a lot better. You can see that the deflection, maximum deflection is 0.00275 inches. Deflections are important. However, you should also look at the stresses because deflection may not give you a good idea, particularly when it's small. If you click on it, the stress distribution, one means the stress distribution is given as 13,000 psi. The maximum is 13,000 psi. Now, assuming that the yield strength of this particular steel is 30,000 psi, then this seems like a reasonable result. Factor of safety is approximately 2. Okay, so we solved this problem using the surface extraction method. I'm going to repeat exactly the same problem with directly generating the sheet metal dope. Okay, so let me close this. Close that. We start with a new file, part file. And since we're going to create the sheet metal or the surface without using solids, we can do that all in the wireframe and surface design where we are right now. So on a particular plane, such as the exit plane here, I'm going to sketch the cross section of that folded sheet metal, which looked like this. Let us give it dimension so that it agrees with what we had before. So this was 1/2 inch, 0.5, and this one was, if I'm not mistaken, 1 inches. All right, exit, and then extrude it. The extrude in the wireframe and surface design is right here. Obviously, you're trying to make a surface. These are different ways of making a surface. The one that we want is extrude. So extrude it by 2 inches. And this is exactly the same surface that was generated for you before. I hope that these dimensions are correct because they look a little bit different from what I had before. Let me look at the sketch here, make sure that we put the right things. Actually, I just realized that this should not be 2, this should be 1. So double click on this, make it a 1, and then exit. And now it's more in line with what we had before. These are the correct dimensions. You can hide this sketch that you use for extrusion purposes. You don't have to join these two surfaces anymore because when you do something like this, you extrude it, it becomes effectively a single surface. These surfaces talk to each other. So let us apply material on it. Apply material, and we made it out of steel, so we might as well go make it out of steel here on the part, and okay. So we are done. Now when we switch to generative structure analysis, since there is no solid part hiding, oh, no, not again. Okay, since there is no solid part hiding, there's nothing in the hiding, you can see that. We have our surface. The Catia will not give you a solid mesh. You don't have to delete the tetrahedral element, the solid mesh, and you don't have the properties. So these are the steps that we had to go through if we actually did it through the surface extraction method. And now we're going to mesh it. We're going to apply a thickness on it, model manager 2D property, and I'll use the same 0.1 that it was the revised value. And now the restraints. So clamp the bottom edge. Yep. And it is actually, the entire bottom edge is fixed. Although when you look at it like this, you may get the impression that only the vertex is. It's not. The whole edge is fixed. And now let us use the planes of symmetry. I'll go through this thing one more time. These faces, these two edges lie in a plane of symmetry which is parallel to XZ. So we go to user-defined restraint, uncheck all of these, and do it fresh. Lies in the XZ plane, there is no displacement in Y, and as soon as you do that, rotations are opposite. And once again, uncheck all of these, select this edge, which happens to be in a plane parallel to the YZ plane. Therefore, there is no displacement in direction X, which is direction 1, and rotations are exactly opposite. Why don't we apply a pressure on it, on this face, and it's actually there, you can see that, except that the direction of it is not okay because of the way things were done. So I'm going to double click on this load and make it -1 so that we push minus 100 psi, so it actually pushes inward. And the rest of the problem is the same, so why don't we just go ahead and run it. And if you look at the deflection, it's pretty much the same as what we had before. All right, and needless to say, if we plot the stress, it's going to be around 13,000 psi. So it's the same problem you're using two different ways. What else do I want to tell you? There is some stuff that I talked about as far as the theoretical aspect of shell goes. That's in the book. You can go ahead and review that. So I'm going to stop the video clip here and we move on. Incidentally, maybe I should say something else. We actually did not have to model planes of symmetry and take a quaternion model. We could have done the whole shebang with a full model. But on the test, you will be asked to use as many planes of symmetry as applicable. If you just go ahead and do it the way you want without planes of symmetry, there is no way for us to know whether you learned what the symmetry conditions are. So just quickly, if I want to do this thing without planes of symmetry, I'm going to kill this. I'm going to kill that. Do it again for you. So start file, new part. On the vertical plane, I will sketch. There it is. Put some dimension on it. So this was 0.5. This was 2. Exit. Extrude it by 4 inches. This is the sheet metal as it was given to you. Okay. We don't have to join it because of the fact that I did this thing directly in wireframe and surface design. I did not create a solid object and then extract the surfaces and things like that. All right, so why don't we apply material on it? Apply material. If we made it out of steel, we go to generative structure analysis. There we are. Clamp the, well, first we have to measure it, of course. Measure the shell element. Let's use the same number. Clamp the edge down here and the edge on the other side. And the edge on the other side, which happens to be this. Since no planes of symmetry are used, then you apply the pressure on this face. The direction looks good. Okay, good. Yep. And run it. Oh yeah, I forgot to put the thickness here. 2D property. 0.1. Now run it. Okay, and look at the deformation or deflections, the displacements on it. To you, this may not be, may not look like the same thing that we had before. However, look at the number. Now, if you want to change the scale so that it looks better, why don't we make this thing actually smaller? So maybe, I don't know, maybe 30. And there, or if you want to make it, let's say 100. Now it's beginning to look like what we had before. It's just that the scale is selected automatically by Catia and just happens to be there. The actual scale of 1, if you wanted to see this exactly with your eyes, scale should be 1. And of course, you won't be able to see any visible deformation here, but they will be, of course. Keep in mind that all planes of symmetry, you need to use them on the final exam. If you do not use planes of symmetry, sufficient number of them, the proper number of them, you will lose marks. Please make sure you understand what this thing is all about, because I noticed that in the lab, in spite of all I said, people were still using solid elements to model the shell. People were still using the full model, and uh, you're going to lose a big chunk of marks if you do that. Okay. All right, guys, let's move on.